Hello engineers. So in this session we'll try to understand the concepts of dimensionless numbers. We'll try to cover all possible dimensionless numbers, that what is the significance of those numbers and how it all are used, and what may be the applications of those numbers. So let's see. So first of all, let's see what is Nusselt number actually. So Nusselt number actually it defines at the uh, actually it defines the ratio of convection heat transfer, I can say, to that of the conduction heat transfer. So it is basically used where the conduction and convection both is taking place. Let's say we have a chip. Okay, let's say we have a chip and it is producing some amount of heat, and it is going towards, I mean, outside the environment, and outside the environment there is a flow of air. So we want that how much heat is convected through the air and how much heat is conducted through that chip. So by that, if we somehow able to calculate the Nusselt number, let's say it is coming out to be zero point 0.1. So it seems that the convection heat transfer is very less as compared to the conduction heat transfer. So in this case we'll try to increase the flow of air. Let's say we can put some fan here so that the convection heat transfer uh, can be increased, and by that we can cool down that device. Okay, so this is the significance of Nusselt number. So here we can derive it like that, because it is the convection heat transfer. It can be written as H A delta T, and conduction heat transfer we can write as K A delta T upon L. I mean, uh, in terms of numericals we can write it like this. Then A can be cancelled out, delta T can be cancelled out, so we can say that it is the ratio of H upon K upon L, or we can say that it is HL upon K, where L is the characteristic length. Okay, we can also say in other words that Nusselt number can be also written as the actually, because it is convection heat transfer and it is conduction heat transfer, though, so we can write it as resistance, conduction resistance, opposite of that, conduction resistance to the convection resistance. So what is the conduction resistance? Conduction resistance is actually L upon Ka, and convection resistance is actually 1 upon H A. So here we can write it as A can be cancelled down, it will come out to be HL upon K. So this is the Nusselt number, and this is the significance of this. So likewise, like Nusselt number, there is also a number similar to Nusselt number, but that is used in mass transfer, that is called the Sherwood number. So as we were comparing the convection heat transfer to the conduction heat transfer, so in the Sherwood number we are actually comparing the convection mass transfer to the mass diffusion, or we can say that the diffusion of mass, I mean, or we can say mass diffusion. So it is somewhat like the heat diffusion through the conductor. It is also like the mass diffusion through some chemical reaction or some chemical reactant. What is the diffusion of the mass is taking place? So this can be also written as the like convection mass transfer. We can write it, it is denoted by H, and mass diffusion rate is denoted by D upon L, where D is called diffusivity. So it is very much similar to Nusselt number, because Nusselt number is showing the relation between the convection heat transfer to the conduction heat transfer. Likewise, Sherwood number also shows the relation between the convection mass transfer to the mass diffusion rate. Fine. Now let's see another number, which is the which is also related to uh, we'll try to relate the heat transfer and mass transfer numbers. So first of all, let's say our third number is the Prandtl number. That is very famous number. We usually know that it is the ratio of the momentum diffusivity to the heat transfer diffusion or thermal diffusivity. Okay, so momentum diffusivity is actually denoted by nu, that is kinematic viscosity, and the thermal diffusivity is denoted by alpha, that is thermal diffusivity. Okay, so why momentum diffusivity is denoted by nu? Nu is actually, it is called kinematic viscosity because the viscosity is the main factor by which the fluid is actually feels the momentum transfer, because this is the, because momentum can be only felt by the in response of the force, and response of the force is felt in between the fluid layers because of the shear stresses, and shear stresses the results the force when it is multiplied by the area between that. That's why it is called momentum diffusivity, because it's somehow relating the forces applied between the layers uh, in response of the momentum diffusivity. That's why it is denoted by nu, and thermal diffusivity we know that it is called alpha. Or if we'll try to expand that, then we can get that nu is actually mu by rho, that is kinematic viscosity to the density of the fluid, and alpha is denoted by k upon rho cp. So we can solve it, and we can get that it can be written as mu cp upon k. When this formula we can directly use, but the main significance point is that Prandtl number is actually tells us that if there is any type of fluid, then we can compare the momentum diffusivity and thermal diffusivity in between the fluid, that how much is the momentum transfer is more or lesser than the thermal diffusion in between the layers of the fluid. Let's say we have a fluid layer, let's say we have a plate, and we have a fluid layer flowing over it, and when the fluid will flow over that plate, then there will be a boundary layer formation. Because of the no slip condition, fluid will stick to the plate, and because of the shear stresses between the layers, there is a boundary layer formation because of the fluid viscosity. But that is if we have the free stream velocity u infinity, but there will also be a free stream temperature of the fluid, and because of that, let's say we have the temperature of the wall plate is Tw, then there will be also a boundary layer formation, that is called the thermal boundary layer, and it is actually denoting that at what extent the temperature difference is significant, because after that the free stream will have only the free stream temperature, and up to some extent we can only feel the temperature gradient within the thermal boundary layer. So it actually denotes that how much is the difference between the boundary layer, viscous boundary layer, to the thermal boundary layer. Fine. Like in case of liquid metals, if I talk about liquid metals, then Prandtl numbers comes out to be very less. It is around 0.001 to 0.004. Okay, so Prandtl number is very less. So it simply shows that the momentum diffusion rate between the liquid metal is much lesser than the thermal diffusion rate. It means that the heat transfer is very much stronger in between the layers of the liquid metal as compared to the momentum transfer. Okay, and in case of water we see that the Prandtl numbers comes out to be around 1 to 1.4. It means that it is around comparable momentum diffusivity and thermal diffusivity is comparable enough. And likewise, similar to Prandtl number, there is one more number which is used in mass transfer, that is called Schmidt number, which is denoted with SC. Okay, Schmidt number. So as we know that the Prandtl number is the ratio of momentum diffusivity to the thermal diffusivity, so Schmidt number also denote the momentum diffusivity, or we can say momentum diffusion to the mass diffusion. So in Prandtl number, the only difference is the Prandtl number compares the momentum diffusion with respect to the thermal diffusion, and but in case of Schmidt number, it shows the, or it compares the momentum diffusion to the mass diffusion rate. Okay, so we can write it like this, like kinematic viscosity to the diffusivity, mass diffusivity. Fine. So it is the relation between the Prandtl number and the Schmidt number, we can say. Nice. Now let's see some more numbers which are somehow related. So the next number is the Fourier number, which is mainly used in heat transfer. So Fourier number is actually basically it is the ratio of the conduction rate. It is the ratio of conduction rate to the thermal storage. So it actually compares that the how much is the conduction through a solid or any material is possible as compared to the thermal storage within it. Or in other word, we can say that, let's say we have an object or we have a material. Fine. So we want to know that if we transfer some amount of heat to this material, so we want to know that how much heat it can be it is transferred by this material, rather than the storing that amount of heat. Let's say a small q amount of heat it stores, and capital Q minus small q it transfers. So we can say that our Fourier numbers is coming out to be capital Q upon small q upon small q. It means that capital Q upon small q minus 1. Numerically we can say. So Fourier number is just signifies that it tells about any material or any object, that how much heat it allows to transfer within it as compared to the storing the heat within it. Fine. So the next number that is somehow little bit related to it, that is called the Stanton number. Stanton number, like Fourier number shows the relation between the conduction rate to the thermal storage, Stanton number also shows that it is the convection heat transfer rate to the thermal energy content. Thermal energy content. It is also a type of energy storage. So because here the Fourier number shows the conduction rate to that of the thermal storage, but here Stanton number shows the convection rate. I mean the basic difference is in between these is the conduction rate and the convection rate as compared to the thermal storage. Fine. So it can be shown like this. Convection heat transfer rate is denoted by H, and heat energy content, thermal energy content can be shown by rho v Cp. So this is the formula for the Stanton number. It can be also written as Nusselt number upon Reynolds number into Prandtl number. If we will put everything within it, then we will get that H upon rho v Cp. That is the Stanton number. So next interesting number is also somehow related with other number. So the next number is the Grashof number. Grashof number we usually study in case of the free convection in heat transfer. So it is basically the ratio of the buoyancy force to that of the viscous force. So basically it shows the relation that how much is the buoyancy force is dominating with respect to the viscous force. Let's say we have a plate uh, which is heated. Let's say its temperature is T wall temperature, and if some amount of air or any fluid is coming out and contacting interacting with this wall, then we want to know that how much is the buoyancy uh, is driven by this the effect of the wall temperature with respect to the viscous forces within it. The whatever the viscous forces between the layers is applied, that how much is the buoyancy force dominating within that layer. That's how the Grashof number is defined. If it means that if Grashof number is greater than 1, it means that the free convection heat transfer is more dominating. Let's say we have a container and we are heating this container and we have some liquid in it. Okay, so because of the viscous effect, the fluid is not moving. Okay, that is still somewhere. But as we are heating this liquid, so because of the heating effect, there will be a formation of some bubbles, vapors, and that formation of bubbles, vapors actually creates the buoyancy force. How? Buoyancy force actually the density of the fluid and the volume of that whatever the vapor is or vapor bubbles into G, that is the buoyancy force. And when it dominates the viscous effect within the layers, then convection occurs because the bubbles rises up or moving from one place to another place. It means that the buoyancy force dominates to the viscous effect, and the Grashof number comes out to be more than 1. Fine. So similarly, there is one more number. They are not, different cases, but this is that other number is somewhat extension of the Grashof number, because it also relates the thermal effect. Here we are saying in Grashof number, we are comparing the buoyancy force to that of the viscous force, but in case of the Rayleigh number, we are comparing buoyancy force to the viscous force and to the thermal diffusion. That the what is the how much buoyancy force is dominated to that of the viscous force and the thermal diffusion. Okay, like in this case, that we want to know that the what is the buoyancy force. Let's say we have calculated the buoyancy force has come out to be rho f vg, which is compared with the viscous force within it. Okay, we have compared, but we also want to know that the what is the thermal diffusion, which is alpha is equal to k upon rho cp. That whatever is the thermal diffusion within the layer, then also because of that thermal diffusion, how much is the buoyancy force is dominating with respect to the viscous force and the thermal diffusion. That's how the Rayleigh number is defined. Fine. And Rayleigh number, if we want to calculate it, then it comes out to be Grashof number into Prandtl number. That is called Rayleigh number. One more number we have seen that okay, further we'll see. Like Stanton number, we have seen that it is the ratio of Nusselt number into Reynolds number into Prandtl number. Okay, so Prandtl number comes out in picture in different places. Okay, so let's say some other interesting numbers like Biot number. What is the significance of Biot number? So Biot number is actually shows the resistance of the conduction resistance of any material to the convection resistance. Okay, like conduction resistance, if we want to calculate, then it comes out to be L upon Ka, and convection resistance 1 upon Ha. So it is actually HL upon K. So it is, basically it comes out with equal to the Nusselt number, but the significances are different, because here Biot number is actually tells about any material. Let's say we have a material and we want to calculate the conduction resistance and the convection resistance. So here we are more concerned about the material, that how much less conduction resistance is there to that of the material, to that of the convection resistance of the material. Because here we wanted to know that if there is a heat generation within the material, then how fast it can transfer to the surface of that material. We are more concerned about the heat transfer within the material to that of the surface. So here the lumped heat analysis comes into the picture. Okay, lumped means what? Some extension of the material. Let's say we have a extended material, let's say a slender rod. Then if we have given heat somewhere, or there is a heat generation within the material, then there it will take very less time to reach to its surface. Or let's say we have a thermocouple in which we use very tiny balls. So we don't want the heat to take time to distribute itself throughout the material, because we want to measure the outside temperature. Okay, so what I want to say here is that Biot numbers tells about it basically focuses on the heat transfer rate within the material, that how much heat transfer can be transferred within the material, so that it can uniformly distribute the heat within the material. Whereas Nusselt number is actually shows the convection heat transfer to the conduction heat transfer to any surface. It is more concerned that how much the convection heat transfer to that surface as compared to the conduction resistance of that surface. So Nusselt number is more concerned about any surface where some fluid is flowing to that of the surface, and Biot number is more concerned about the heat transfer within the material. Fine. So our next number is the Lewis number. So Lewis number is actually is the ratio of the thermal diffusivity to that of the mass diffusivity. So it basically shows the relation between the how much is the heat transfer can be taken as to that of the mass diffusion. I mean, let's say we have some reactant or any chemical material we have, and we want to know that, and some chemical reaction is taking place within that material, and because of that, let's say some chemical reaction, because of that chemical reaction some heat is also generated. So we want to know that what is the ratio of the thermal diffusion to that of the mass diffusion. I mean, how much thermal diffusion is dominating to the mass diffusion of that chemical reaction. So it basically deals with the chemical reactions where the heat is also taking place. Fine.